Good morning, physics. Today I'm going to show you guys how to solve Unit 3 practice exam. I'm going to walk us through it. Please use this as you're working through your corrections. So we look at problem 1. We have a 60 kilogram ice skater holding a 20 kilogram box. Those are both masses, so I'm going to call this mass 1 and mass 2. And together they're moving with a velocity of 4 meters per second. Okay? That word holding means that they're together. She needs to throw the box in front of her to come to a stop before she reaches a hole in the ice. How fast does she need to throw the box? I see M and V. This is also starting together and then moving apart, which is a recoil. So I can set up P1 plus P2 equals P1 prime plus P2 prime. This is what we call conservation of momentum. So now I'm going to put it in long form. And now I'm going to plug in the numbers. So we've got 60 and 4, 20 and 4. She needs to stop, so that means her velocity is going to be 0. The box doesn't lose any velocity, and that is ultimately what I'm going to solve for. Okay? So at this point I would go ahead and work it out on my calculator. I get 320 on the left side equals 20 V2, divide, and V2 is 16 meters per second. Okay? So the correct answer for 1 is D. Number 2. We see a 1 kilogram cart that moves at 4 meters per second, so I've got a mass and a velocity, collides inelastically with a 2 kilogram mass, and since I have two masses now, I'm going to call one mass 1 and the other mass 2, which is initially at rest. That's telling me a velocity. Which of the following statements is not true about the momentum? So inelastic, we know, means two things. 1, momentum is conserved, but 2, kinetic energy is lost, or is transferred out of the system, rather. Okay, so it is not conserved. So what we're essentially looking at is that we have, a cart that moves, or a mass that moves towards another cart that's at rest. Something happens, and what we want to know is afterwards. Okay? Let's start with option B. Before the collision, the total momentum was equal to the momentum of the 1 kilogram cart. That's going to be true because this is the only cart that's moving. Cart 1 is the only cart that's moving. So the momentum here is 0, so all of the momentum in the system is in cart 1. After the collision, the 2 kilogram cart has more momentum than the 1 kilogram cart. Well, that can't be true because we're taking this 1 and we're splitting it into 2. So they both would have to have less than this cart started with. So that's out. And the initial momentum of the 1 kilogram cart is now shared by the 1 and the 2 kilogram. Well, that's what we just said. That's how we justified B and C. So D is out. A is the correct answer. We know that if 1 hits 2, 1 has to slow down as a result. So it's not going to have the same momentum after the collision. Also, 2 was not moving. It would be moving after the collision, so it's not going to be the same either. Let's move on. Number 3 talks about a flat railroad, or a railroad flat car. It's got a mass. It's got mass on it. Rolls to the right with this momentum. So we're actually given a momentum, and collides with another flat car that's rolling to the left with another momentum. I see two momentums, that's P1 and P2. We want to know total momentum after they collide. Total just means add, so I'm going to do P1 plus P2 to get P total. So that's 20,000 plus negative 15,000 to get P total. You could put that into your calculator or do it in your head. 20,000 plus negative 15,000 gives you 5,000 kilogram meters per second, which is P total. Okay? So the correct answer is A. Let's keep going. is a old circus trick. You would take a person, put them into a cannon, and fire them. So we've got this really heavy cannon. We have this person that's very light. The person out of the cannon shoots with this velocity. One of the rules we need to remember, the bigger mass has a smaller change in velocity. That's just always going to be a true rule. So if the man's velocity is 15 meters per second, this is much smaller, so this velocity would also have to be much smaller. Okay? Now, which of the following must be the same? First one is the force. That we know is true because of Newton's third law. For every action, there's an equal and opposite reaction. Impulse is Ft. Well, because the force is the same and they're being fired at the same time, this is also true. The magnitude of the change in momentum, now that's saying how much momentum this guy had is going to be equal to how much momentum this guy had. We'll come back to that one in just a second. The change in the speed, that we know is not going to be true because of this right here. The bigger mass has a smaller change in velocity. So they went from 0, this guy went from 0 to 15, the cannon went from 0 to something less than 15. So we know that this is not true because of our rule right here. Okay? Now, talking about the change in momentum, we know that P1 plus P2 equals P1 prime plus P2 prime. Okay? So, at the beginning, they're attached together. The momentum, the total momentum, is 0 and 0. So if at the end we have positive 15 and 100, that's going to be 1500. Well, I need this cannon to make this 1500 equal to 0. So the opposite of 1500 is negative 1500. So it turns out that the amount of change in their momentum was the same. We went from 0 to 1500 and 0 to negative 1500. So 3 is also correct. C happens to be the correct answer. And that one's a little bit more tricky. Let's keep going. Number 5. We've seen a couple examples of this in class. Spring constant, that's little k, and we're going to double it, which is multiplied by 2. What happens to its stored energy? That's a fancy way of saying potential energy. So let's write our equation. 1/2 doesn't change. Spring constant is doubled. Stretch distance doesn't change. So the change in the stored energy is doubled. So that's C. Number 6, we have a rock. We're going to drop it off a cliff. Now this is the one I think where most people struggled because I give you another height after falling 20 meters. We want to know what the kinetic energy is. So again, this is where a picture is going to help. I have a 90-meter cliff. It's pretty tall. I'm going to take a rock and I'm going to drop it off. Now after it's fell 20 meters, I want to know what K is equal to. Now, we don't care about how far it fell, we care about how high it is. So if the whole cliff is 90, it's fallen 20 meters, that then means it's 70 meters above the ground. That's going to be helpful in a second. Okay? So all we do is UGO plus KO. There's no spring, so I'm not even going to write it, equals UGF plus KF. At the beginning, the rock is dropped, so that initial kinetic energy is 0, because dropped means the velocity is 0. It's not thrown, it's dropped. So I'm going to do mgh equals, now at the end, it hasn't hit the ground yet, so it still has potential energy, but if you think about when you drop something, it starts to move. Once it moves, it now has kinetic energy. And it's not asking about the velocity, it's asking about the kinetic energy, so I'm going to leave this as K, not 1/2 mv squared. So we have a 1 kilogram rock, 9.8 is G, our initial height is 90, 1, 9.8, and now my new height is only 70. So let's solve for KF. I'm going to plug this into my calculator. I get 882 here. I get 686 plus KF. Now I'm going to subtract on both sides, and that gives me 196 joules. Go ahead and round that up. There we go. Another way you could have thought of it, take your initial potential, subtract how much you lost, whatever is left over is your kinetic. Both ways work. Number 7. We have a mass spring with a spring constant K is compressed 5 centimeters. Okay, pay attention to your units. Right away, I'm going to divide that by 100, and I get 0.05 meters, because I know I'm not going to use centimeters in my calculation. From its equilibrium position by a mass. So basically it's just stretched. How much energy is stored in the spring mass system? Okay. So here's the thing. The mass actually isn't useful because we only have one type of energy, and that's elastic potential. So I'm going to plug in everything that's given to me with my converted stretch distance, 0.05. Let me see if I can get this to focus again. And now I'm just going to plug this into my calculator. So 0.5 times 1200 times 0.05 squared, and I get a stored energy of 1.5 joules. So, piece of cake. Number 8. We have 2 students conducting a lab to determine the amount of energy stored in a spring. Okay, so we want to know US. They compress the spring and use the spring to launch a ball straight up into the air. So we're going from US to UG. If they measure the mass of the ball, what other measurements could they make to determine the initial energy stored in the spring ball system? So I'm going to write this in equation form. I know that this whole value has to be equal to this whole value, right? Because I'm taking this energy and turning it into this. They already know the mass. Okay, so they're actually measuring stuff over here. They don't even need to know anything about this. G they already know, so the only variable they're missing is h, so I don't need to know the velocity, I don't need to know the weight because I already know the mass, so all I need to know is the maximum height reached by the ball. Okay? Whenever you're doing these lab-based problems, figure out how the energy or the momentum is moving, write out your equations, figure out which variable is given, and then work from there. Next, number 9. They're doing a recoil collision. This is the one I showed us in class. Okay? No, they have different masses. We'll see that this doesn't matter in a second. They start at rest and they're pushed apart with the spring. So this is identical to what I did. You push the little plunger, the spring comes out, they go in different directions. If the final momentum of cart B is negative 2.4 and momentum was conserved, what's the final momentum of cart A? So it turns out their mass doesn't matter. If B's momentum is negative 2.4 kilogram meters per second, and they started together at rest, okay, this is just like that earlier problem. We know that P1 plus P2 equals P1 prime plus P2 prime. If they start at rest, their initial momentum is 0. Cart B has negative 2.4. So cart A needs what to make 0? Just positive 2.4. So C is the correct answer. This is identical to our cannon problem right here. Or at least you have to apply the same thing. Okay? Alright. On to 10. We have a problem about Robin Hood. He shoots an arrow at an apple. The apple is initially at rest. We have a 0.2 kilogram arrow that has an initial velocity of 40, and it sticks to the apple. So that means they have the same final velocity. This also tells me it is a totally inelastic collision. In fact, it further tells me if the final velocities of the arrow and the apple are both 10 meters per second, what is the mass of the apple? Okay. So this is a collision. I'm going to use conservation of momentum. I'm going to break up my variables. M1 V1 plus M2 V2 equals M1 prime V1 prime plus M2 prime V2 prime. Now let's go ahead and plug these in. We have a 0.2 kilogram arrow traveling at 40 meters per second. The apple is initially at rest. I don't know its mass, so I'm going to call it M2. The arrow at the end is only moving at 10 meters per second. The mass of the apple, again, is what I'm solving for. It didn't change, so I'm just going to call it M2. Same as before. And the final velocity is 10. Well, anytime we multiply something by 0, it's gone. So we have 8 equals 2 plus 10 times M2. Subtract 2 from both sides. And the mass of the apple is about 0.6. Oops, sorry, I went off the paper. Subtracted 2, 6, divide 10 on both sides. The mass of the apple is 0.6 kilograms. So there we go. There's our answer. Okay, we have a graph problem. The situation is one that I showed us in class. We have a pendulum attached to the ceiling, just like I did in class, and it's swinging back and forth. You can't really see, but there was supposed to be another drawing right there. Okay. So here we go. At 2 different times, we have energy value at 3 seconds, energy value at 5. The question just asks, was energy conserved? For energy to be conserved, the total initial energy must equal the total final, which means the total should always be the same. So this problem actually ends up being pretty simple. We're just going to read the graph. Now, on the unit exam, these will have lines, so you don't have to guess, but we see 11 joules here. That's 8 plus 3. We have 7 and 2 here. That's only 9 joules. It looks like energy was lost or transferred out of the system, so the total initial does not equal the total final, and energy was not conserved. So A and B are out. Now I just need to check and see which one, C or D, is correct. So it's not because the kinetic energy values changed. That's always okay. Okay, your kinetic energy can change. The pendulum moves faster at the bottom than it does at the top. Remember, it swings and then it slows down and stops, and then it swings back down and stops. And so that kinetic energy is always changing. The important thing is the total. Okay, so D is the correct answer. C is out. Number 12. Number 12 is another funny one. We haven't seen a graph like this that looks like this, but it is just a velocity time graph. Okay, so imagine this skateboarder. Here's the thing. The skateboarder is basically just a pendulum. So he goes quickly this way, slows down, stops, goes quickly this way, slows down, stops, and back and forth. And so sure enough, that's what we see. He speeds up, goes really quick down at the bottom, then he goes down and stops near the top. Then he comes back down the other way, speeding up, and right here, and then he starts to slow back down at the top. And so he just keeps going with this motion. So this would be in the middle, this would be at the top, all the way across. Okay? So the question asks, when does it most likely have equal amounts of kinetic and potential energy? Well, at the middle, his potential energy is 0 because his height is 0. He's down at the ground. At the top, his kinetic energy is 0 because he's stopped up here. So right in between those two is when he's going to have equal kinetic and potential energy. So that's going to be somewhere right here. Well, the point closest to that is R, and sure enough, R is the correct answer. All right. We have a rocket. The way that rockets move is they shoot out gases. Okay, that's the fire that we see underneath. It's just really, really fast moving gas. So the question asks us which is true. Okay, whenever you see a problem involving something like this, most likely I'm going to be asking you about forces, because again, people don't understand Newton's third law. So, A, the force of the exhaust gases, so it would be the force of these pushing up on the rocket, must be equal to the force of gravity. That's not true. If the gases pushing up were equal to the force of gravity on the rocket couldn't accelerate. It would be in equilibrium. A is out. For B, the force of the exhaust gases on the rocket must be greater than the force of the rocket on the exhaust gases. So now we're talking about two objects. We're saying that the force of the gas on the rocket must be greater than the force of the rocket on the gases. Well, we know that this completely negates, or it's opposite, Newton's third law. This force and this force should be equal because they are action-reaction pairs. So B is out. Okay. So let's take a look at C. The magnitude of the acceleration of the rocket and exhaust gases must be the same, since the magnitude of the force between the rocket and the exhaust gases must be equal. So now they're saying that the force between them is equal, which is true, but the acceleration of them is not true. Okay, those do not need to be the same. Although they have the same force, the mass of the rocket is very big, so it has a very small acceleration. That's why it takes rockets a little while to get up to the sky, right? They have to fire this for a long time, and then they just barely start to move, and then they go up. For the gas, though, the gas has a teeny tiny mass, the same force, therefore its acceleration is huge. That's why we see that fireball come out of the bottom. So C is out, even though it was close. So the underlined part is correct, the circled part is wrong. That must mean D is the correct answer, but let's make sure. The force on the exhaust gases on the rocket will be equal to the force of the rocket on the exhaust gases. That's true. That's our action-reaction pair. That's telling me that the gas pushing up on the rocket is equal to the force of the rocket pushing down on the gas. Those need to be equal, and they point in opposite directions. And then in the opposite direction to allow the rocket to accelerate upwards. That's true, the rocket is accelerating. Okay, so there's confirmation. Okay, 14 looks like a really complicated diagram. Turns out it's a pretty simple one. Okay, so if we look at this situation, we have a spring and we have a mass. In one case, the spring is down here on the ground, and the other one, the spring is vertical. Okay, we have equal masses. In trial 1, it's released from the top of a ramp. In trial 2, it's just released from a height and it falls straight down. Okay. The question is, in which trial will the spring compress a greater distance? Okay. So this is just a conservation of energy problem. We're starting with UG. We end with US. Okay. Here's the thing. In trial 1, the mass gets to have a height difference from here all the way down to here before it hits the spring. In trial 2, it hits the spring right here. So the change in UG is much bigger in trial 1 than it is for trial 2. That means then less energy gets transferred from gravitational to elastic here than here. So before I even look at the answer choices, I already know all of this. So let's see. So based on just this description, it should compress more right here because it's traveling a further distance. So A says in trial 1, more of the initial energy of the block Earth spring system will be converted into the elastic potential energy. So that's true, but let's make sure everything else is false. Because in trial 2, because the force of gravity will cause the mass to exert a greater force on the spring. Well, that doesn't make any sense because we know that both of them are going to experience the same force. So that's out. for answer choice C, the spring will compress by the same distance. We know that's not true. Let's just make sure why. The total energy of the block Earth spring system must be conserved. That actually is true, but it's not going to compress by the same distance. And finally, the spring will compress by the same distance. We know that's wrong, since each trial had the same mass. Now, that is important. They do have the same mass, and we know that UG is mgh, but the H is different, so they're not going to compress the same amount. So A is, in fact, the correct answer. Let's take a look at the griddable. The griddable has a spring-loaded cannon, just like we used in class. We're going to launch a 0.4 kilogram mass at a target. The spring in the cannon has a spring constant of 80 newtons per meter. How far will it have to be compressed to launch the mass with a velocity of 20 meters per second? Round your answer to the nearest tenths. Okay. So we are taking US and we're turning it into K. So I'm going to do my conservation of energy. I don't need to worry about UG on either side because we're not talking about height. And the mass is going to start at rest because it's sitting in the cannon. And it's not going to be touching the spring at the end, so there's no US over here, so I can skip a bunch of steps. So I'll write my two equations, and now we just plug in and solve. Got 80 here. I'm going to solve for x. I know my mass. I know my velocity. So I'm going to plug all this into my calculator at once. It's 200 on this side. I'm going to do half times 80. Divide both sides by 40. Take the square root. And that gives me x equals 2.24 meters. Not very realistic. We're never going to stretch a spring 2 meters long. But if you wanted to get something to launch at 20 meters per second and it was a weak spring, you'd have to compress it pretty far. Okay. Now it says round to the nearest tenth. That would be here. So what you would actually put on your griddable is 2.2. Okay. Good. So that brings us to the end of multiple choice. Let's take now a look at the free response. The free response has another cart situation where we're going to take cart A and cart B and we collide them into each other. It's on a frictionless surface, which is good. That just makes the problem easier. We know that cart A has a mass of 0.3 kilograms and cart B has a mass of 0.5 kilograms. And in the first trial, they're going to move together. Okay? So cart A has an initial velocity of 6 meters per second. Let's find the initial momentum of cart A. So P equals mv. The mass of cart A is 0.3. Its velocity is 6. 0.3 times 6. That just gives me a momentum of 1.8 kilogram meters per second. Now, you need to write this in the box. Write your answer in the box. So 1.8 kilogram meters per second. Now we want to find in part B the final velocity, the initial velocity of cart B. We want to see how fast it was going at the beginning, now that we're given how fast it was going at the end. So let's set up conservation of momentum. Okay. We know the initial velocity of cart 1, so we can actually set this up. Before we do that, let me get into the long form. v1 prime plus m2 prime v2 prime. Okay, let's plug everything in. Mass of cart 1, 0.3. Velocity at the beginning, 6. Mass of cart 2, 0.5. Velocity at the beginning. That's what we're solving for. Mass of cart 1 didn't change. Velocity at the end. So here's the thing. It tells us cart B has a velocity of 2, but but they stick together. That's another key in here. So if they're stuck together and cart B has a velocity of 2, cart 1 also has a velocity of 2. Now I'm just going to do the math. So give me a second while I plug this into my calculator. This is 1.6. We know that this is 1.8 plus 0.5v. So we're going to subtract 1.8 on both sides. We get 0.5v equals negative 0.2. Divide by 0.5 on both sides. And your velocity is negative 0.4 meters per second. So negative 0.4 meters per second. And that should make sense because at the beginning, cart A is moving to the right, cart B is moving to the left, so its velocity should in fact be negative. Okay, now in their second trial, they're going to make a couple adjustments to their lab. Their adjustment is such that they end up at rest after the collision. Okay? So their kinetic energy at the end is 0 joules. Okay. The question is he correct? Well, if they end up at rest, the final total kinetic energy we know is 1/2 mv squared. If both of them have a velocity of 0, then even if I were to add 2 of these, if both velocities are 0, the total is going to be 0. So we would say Diego is correct because if the velocity of both carts is 0, their total kinetic energy is also 0. Okay. Good. Let's move forward. So now it says during the collision, cart B experienced a force of 20 newtons. Is the magnitude of the force experienced by cart A greater than, less than, or equal to 20 newtons? Justify your answer. This is a fairly simple one because of Newton's third law. We would say cart A would experience the same force because of Newton's third law, which states the force between two objects is always equal and opposite in direction. Okay. Good. Now let's bring it on home. They now replace cart A and B with two different carts, C and D, and they bounce apart as they collide. They place D at rest, and then they push C towards D. So the initial velocity of D is always 0. And they push cart C 1 meter per second. In each trial, they add mass on cart D, and this shows the final velocity for C. Which trial will cart D have the greatest final velocity? We need to remember a rule that I talked about way back in the multiple choice. I said the smaller mass has the greatest change in velocity. Okay? So let's figure out then what's the change in velocity of cart C. So cart C has a so to find it, we're going to do final minus initial. So for trial 1, the final is negative 1.1. We're going to subtract 1 from that for a delta V of negative 2.1 meters per second. And then 0.2 minus 0.1. Let me make sure my math brain is off today. This is negative 0.8, so that's a smaller change in velocity compared to this. And then the last one, 1.4 minus 1, gives us a delta V of 0.4 meters per second. Okay. So, based on this, we can now start to make some claims about cart D. Okay. Give me just 1 second. I just want to be sure I'm correct about this. Okay. So the other thing to note is we want to consider the conservation of momentum. So that P1 plus P2, those totals are equal at the beginning and at the end. Okay? So because cart C hits cart D and goes in the opposite direction, the bigger the momentum is over here at the end, the bigger the momentum over here has to be at the end. Okay? So what we would say, biggest change in velocity happens here. So our claim, trial 1 has the, or in trial 1, cart D has the greatest final velocity. Okay. To get our evidence point, we need to reference the table. We would say in trial 1, cart C has the greatest negative velocity, and then I actually need to include the number, so I'll put it in parentheses. In the other trials, cart C has a positive final velocity, or just velocity. And then again, I'm going to put it in parentheses to get my evidence point. So now let's wrap it up all up. This is where you use the physics law. So according to the conservation of momentum, the greater the negative velocity for one cart, the greater the positive velocity for the other cart. Okay. By putting this, you would get maximum points for your CER. Okay. All right. So use this to correct your exams. Feel free to ask me if you have any questions.